So when your front end has detected that your program is error-free, so again, just considering the one compilation unit, the one C file you're compiling, it can generate an intermediate representation. So an intermediate representation is an internal representation of your program that's somewhere in between the level of your high-level language of C and the level of your machine code. So it's independent of your source code language, but it's also independent of your machine code language, and it's on a level that makes it easier to optimize the code. So your optimization steps can be simple, can be general, and work for many different languages and machines. So IR is the data format, just interfacing the front end, doing the analysis and error checking, and the back end, doing the program code generation and optimization. So IR very often comes as a data format, like a binary format, or in the case of LLVM, you also have a textual format that very much looks like assembler, but isn't quite assembler code. And IR is also, of course, a defined language that is used to express syntax and semantics of a program. So why do we want another language? Early compilers directly generated assembler code from your source code and were happy with this. But this made it hard to optimize information. For example, if you generate machine code, assembler code for ARM, you don't have any type informations left. So you don't know if this data you're operating on is actually an integer or just a character or something else. So assembler code does not have enough information to optimize the code well. Intermediate representation retains some of this information, so you can do more reasoning about the semantics of your code, and you also enable modularity and reuse. Of course, when you want to write a compiler nowadays, you have different source languages. So for example, you not only want to write a C compiler, but you maybe also want to write a C++ compiler, or a Rust compiler, or a Go compiler, or even a Java compiler. Now, on the other hand, you have different target architectures. You have, for example, Intel processors, you have ARM processors, you have something else, a RISC-V, or whatever you can imagine. And if you wanted to write a C compiler for RISC-V, and a C compiler for ARM, and a C compiler for x86, early on you would have to write 3 different compilers, and then if you wanted a C++ compiler, you'd have to write 3 additional compilers, and so on and so forth. Using the intermediate representation, you can reduce your work. You can just write a front end that parses and understands C and generates intermediate representation code. You can write another front end that parses and recognizes C++, generates intermediate representation, and so on. And from this intermediate representation, you can generate x86 code, ARM code, and so on and so forth. So you split up the tasks of the compiler by introducing this intermediate representation, and instead of requiring n times m for source and target languages compilers, you only require n plus m front ends and back ends. So if you actually only want to write a compiler for a new programming language, my great programming language, you just have to write a front end if you can find a compiler that understands your intermediate representation, and you can make use of existing backends. This is, for example, the idea behind the Clang and LLVM toolchain. So this is based around a common intermediate representation, and this intermediate representation allows you just to write your front end and make use of all the code generation and optimization stages that exists for a target architecture. Or on the other hand, if you just implement a new processor with a new instruction set, you can just write a new code generator here, and you don't even have to write all the optimizations because they work on intermediate representation, and you don't have to take care of writing a front end because a front end generating IR for C, for example, already exists. Now, how is this intermediate representation structured? So you want to represent 2 things. You want to represent how your data actually propagates throughout your program, and you want to represent how your control propagates throughout your program. So the first thing you want to do is to create a so-called data flow graph, or DFG, and this data flow graph represents flow of data inside what we call a basic block. Now, what's a basic block? A basic block is essentially just a sequence of machine instructions, but this sequence of machine instructions comes with some restrictions. Essentially, it's an uninterrupted sequence of machine instructions. So it means it's code where you can only enter this piece of code at the beginning, so you can only jump to it when you jump to its start, and it ends usually with a branch or just with the end of a program or something like this, but it cannot have a branch in between. So all branches, all jump instructions you have inside of your intermediate representation, for example, in a basic block, just ends this basic block and starts a new one. So basic blocks just represent uninterrupted sequences of calculations, so how your data is actually transformed, for example, by adding two values together. It does not represent any form of control flow inside of your program. Data flow graphs describe the minimal order requirements on your operations. So if you add two values and then multiply the sum you just calculated with some other value, you need to add first, and then after that you can actually do the multiplication, but not the other way around. And to enable optimizations, we use a very specific form in our intermediate representation, and this is so-called static single assignment to ease the optimizations. So very often in programs you reuse variable names like x several times, and that makes it very difficult to figure out if this value of x is an old value or if it's a newly assigned value. So static single assignment solves this problem. Static single assignment, if a variable is assigned to more than once in your source code, only keeps the first assignment, and the rest of the assignments are just renamed, so you give them an additional number. So the first assignment of a variable x is just called x, and the second one would be called x1 or something like this. So we have an example for a basic block here. You see it's a valid basic block. This is C source code, obviously, and we don't have any jumps in between. There's no goto, there's no control structures, there's no if, no while, no loops, and so on. And so it just does a number of calculations, so just your data flows. So it flows from A and B are added to give the value of x, then C and D are used, so D is subtracted from C to assign the value to y. Then these two values here, x and y, are multiplied together to give the value of z, so we can't execute this multiplication before we've executed these two instructions up here. And then finally, values of b and d are added together again and assigned to y. Now, x and z are not problematic here, but you see y is assigned here and assigned another time here. So the old value of y, which is used here, is no longer useful here, so you reassign y, but your compiler has a hard time finding it out because these variables, of course, have the same name. So we need to tell our compiler, or to help our compiler, to actually better understand this. So we do this by just renaming the second instance of y to, for example, y1. So we now know that this y here is not occurring anymore. So we assign this again to y1, and our compiler then knows, okay, this is a new instance of a variable, so the old value of y is not available anymore after executing this instruction. So this is called static single assignment. Single assignment because we only do it once, so we only assign to each variable once, and it's static because, yes, it only happens in the places where we do the assignment. So now we can transform this piece of code in static single assignment form to a so-called data flow graph. So a data flow graph consists of operations, so like here arithmetic operations, and these arithmetic operations take integer or variables as input and output some other variables. So for example, the first line of code x equals a plus b is transformed into this block here, so we have our addition operation. We take a and b as an input and we output a variable called x. The next line of code, y equals c minus d, is represented on the right hand side here, so we have a subtraction operation here. We subtract d from c and generate an output we call y. Then we have a data dependency, so z requires the values of x and y. So we have errors just combining the output values of this addition and this subtraction operation here, and using them as inputs to our multiplication operation, which gives us the value of z. And the last line takes the input variables b and d again, so we have additional arrows going from b and d down here to our next addition operation, and that now gives our value of y1. This is our data flow graph that describes how data dependencies actually run throughout our basic block here. Now, in modern processors, you often have superscalar execution. So, for example, you can do an addition and a multiplication or two additions or whatever in parallel. So, in order for a compiler to determine which operations can be safely executed in parallel, you can define so-called partial orders. So, for example, you see that this addition operation and this subtraction operation are not dependent on each other. So, since they're not dependent on each other, we can execute them in parallel if we have enough functional units available in our processor. However, this multiplication operation requires the results of this and that operation here. So you cannot execute the multiplication operation simultaneously with the addition and subtraction because the results of these two operations are not yet available to our multiplication. So we have a partial order. Our multiplication must take place later than addition and subtraction up here. So we have a partial order. We can execute a plus b simultaneously with c minus d, and we could execute x times y simultaneously with b plus d. Now if you look closely, this addition also has no data dependencies on any of the previous operations. So if we had 3 functional units available, we could actually execute this addition also up here, because there's no data dependency to any other operation, just to the input variables, which are assumed to be available at the start of our program at all. So this could be, for example, a typical sequence of operations. If we have 2 functional units, 2 ALUs available, we could do the first addition and subtraction simultaneously, and then do the multiplication and addition simultaneously. If we had 3 functional units, we could move that one here, b plus d, up into the first operation and maybe do something else, which is not specified here, in parallel to our multiplication operation. This would depend on additional code that we have not given here.